So today we'll be discussing about the deadlock, a new topic. As I told in my previous class, we have completed this process synchronization. Now we are going for this deadlock, which is a very, very important chapter, and problem will definitely come from the deadlock actually. Okay, so today's topic of discussion is deadlocks. I have already given you a brief introduction, small introduction about the deadlock earlier. And I have also told you about a starvation. So before going to the deadlock, let me first tell you what actually a starvation is, because starvation I have not included over here in the slide. So anybody who can say about the starvation? Anybody who knows the starvation? Anybody who can say what is starvation? We have already discussed the starvation, why it occurs. Anyone? Hello?
Sir, when it is not able to, when it is able to come out from the critical section after going through the signal.
It is not coming to the critical.
After coming out from the critical, deadlocks are unable to come out from the critical section, but starvation can come out of the critical section.
I will tell you, it's not exactly the answer, but I will tell you that what is that. Anyone else can say? Anyone else who can say what is starvation? Starvation occurs if a process is indefinitely postponed. This may happen if the process requires a resource for execution that is never allotted and the process is never provided the process of the same. Okay, the first part of your answer is correct. Starvation occurs, Banishri. Starvation occurs if a process is indefinitely postponed. This may happen if the process requires resource for execution that is never allotted, or if the process is never provided the process for some reason. Anyway, I will just accommodate all this. Before that, let me write something over here so that I could explain. In the meantime, if you have any, because there is a slow in yes, the priority allocation. Okay, so let me tell you what actually this starvation is. The starvation says the starvation occurs when a process is denied of a resource continuously. When a process is denied of resource continuously, then it is called a starvation. Correct? But the process is ready to acquire the resource. The process, try to understand all of it. Process is ready to acquire the resource. Process doesn't have any problem. The moment the process makes a request, at the same time, some other process may make a request and take it. This is because of its bad luck. You went to a shop. Suppose you go to your Ashok shop and you are requesting for something to Ashok. At the moment you are requesting, there is one copy of that thing is there, the moment you request, somebody will make a request and take it at the same moment. Exactly just before that, somebody will make a request and take. That is your bad luck, right? Second one is the priority allocation. The moment you make a request, somebody else having the higher priority, a staff will come and make a request and get it, or teacher will come make a request and get it. It is a priority allocation. So process may get the resource, but process is unable to get it because of bad luck or priority allocation. So bad luck and priority allocations are two reasons for starvation. Is it understood? Note it down. Bad luck and priority allocations are two reasons for starvation. I have not included in the slide. I forgot to include. I will include it. So bad luck and priority allocations are two reasons for starvation. Correct? In starvation, we cannot say that this process will never get the resource. Process will get a resource whenever somebody will finish, it will return, and the process may get the resource. But deadlock says that it is a situation in which the process is in a circular queue waiting for each other, and none of them can continue indefinitely. If you would leave them like that, they will never continue. Correct? In starvation, what I am saying, the process is waiting. Some other process may make a request and get it, or some bad luck or priority allocation will occur. Process may not get, but we cannot say process will never get. But in deadlock, if the same situation occurs and all are waiting for each other, then they will never continue. I will give the example of deadlock. So for the time being, so starvation occurs because of bad luck or priority allocation. Now question is that how to avoid this bad luck? How to avoid this bad luck? What will do over the solution for the bad luck is a queue. The solution for the bad luck is a queue. Suppose the Ashok shop will say that whoever is making a request, you come in a queue only. I will serve only in a queue. So everyone will definitely get a chance. Right? Everyone will take and it will return. The next one you come and take. So the solution for the bad luck is a queue. We can maintain a queue over there. The solution for priority allocation. So this is a queue over. We can use a queue over here. Q. And what is the solution for priority allocation? The solution for priority allocation is aging. I already told you what is aging. Aging is the process of gradually increasing the priority of the process. Aging is the process of gradually incrementing the priority of the process. So now suppose a student is making a request, is having the lower priority, but after continuously 2 or 3 denials, his priority may be increased. Okay. So if he or she will be denied, again the priority will be increased. So after a particular number of denial, the priority of a process may be increased. So starvation, the solution to the starvation is there. You have, it may occur due to bad luck, it may occur due to priority allocation. Bad luck can be avoided by using a queue, by implementing a queue. Priority allocation can be avoided by using the aging technique. Aging technique is continuously, gradually incrementing the priority of the process. These things you remember. Usually comes what is aging, or which technique is used to avoid priority allocation. Or starvation occurs due to priority allocation. Is that clear? I hope it is understood. The starvation is understood or not? I will give the example for deadlock. Is the starvation understood or not?
Yes, sir.
Okay. So we'll go for deadlock. In our practical, in a real life situation also, we find there are some situations where none of the process can continue. This is a traffic scenario. You can see that this scenario sometimes occurs, where each of the vehicle is waiting for the next vehicle to continue. right? So if they will stand like this, none of them can continue at all. If the condition is that none of the car or vehicle want to go back, they don't want to release, they don't want to go back. Can this problem be solved ever? None of the vehicle wants to go back. They don't want to revoke their resources. Can it be solved? Do you think this problem can be solved? If none of the resource, none of the car will go back?
No.
No. Let us give one more example over here. Suppose this is your library, right? This is your library. To the library, two of the students, they have taken two books. One has taken the Galvin book of operating system. One has taken Galvin, and second student has taken suppose Godbole book. Godbole is a popular book on operating system, right? So Achyut Godbole book is over here, right? So a student has taken Galvin book. There is only one copy of Galvin and one copy of Godbole is there. Try to understand. There is one copy of Galvin and one copy of Godbole is there. So first book is allocated to the student A and second book is allocated to student B, right? This is allocated. Now the student A wants, I must return the Galvin and I want to get the Godbole book. Try to understand. A wants to return the Galvin and wants to acquire the Godbole, where the student B wants to return the Godbole book and wants to acquire the Galvin book. But both are very clever. They both are very clever. What they want that whenever I will get the next book, then only I will release the current one. Otherwise, I may not get the previous one. That means student A wants the Godbole book, but it wants that I will get the Godbole book and I will return the Galvin then. So it is holding Galvin and requesting for Godbole. But the student B is holding the Godbole book and requesting for Galvin book. Is it understood? That means it is holding something and requesting for another one. Whenever the second one it will get, it will release the previous one. Hold and wait. It is holding something and waiting for another one. They both are standing in front of the library. Correct? Do you think they can return and get their books? Do you think they can ever return their books? Is it possible to return their books and they will get their next book?
No, sir.
No, definitely not. If they will stand there for years and years, they will never get. The reason is that they are not ready to give their books, whatever they are holding. And this is something like, both are dependent on each other. The both are dependent. It's a circular weight kind of thing. This is a circular weight kind of thing. Is it understood? One more example I am giving. Suppose in your college, a classroom, the classroom is, suppose this is 303. This is room number 303. And there is another classroom, this is 452. Correct? There are two different classrooms. A notice has came from the director that a teacher can only leave a room. A teacher can only leave a room whenever the next teacher is at the standing in front of the room. That means when the next teacher will arrive, then only the previous teacher can leave. Try to understand. The order is that a teacher can only leave whenever the next teacher is available or standing in front of the room. A teacher A and is taking class in 303, and a teacher B who is taking class in 452. Correct? The teacher A has the next period in 452, whereas the teacher B has the next period in 303. Correct? The teacher A is taking class in 303, the next period is in 452. The teacher B who is taking in 452, the next period is in 303. Can they ever leave the room? Can they ever leave the room? They can't ever leave the room. Because, why is that? Because they are, each one is waiting for the other to occur. The 303 is over here. He is waiting the B to come so that he will leave the room. B is waiting over here for A, and if the A will come, he will release the room. So both will stand in the room for the entire day, but they cannot leave that room. So these are the state of deadlock, where none of the process could able to continue. It is not starvation, it is deadlock. They will never continue, right? Indefinite period of blocking. Indefinite period of blocking there. Correct? They will never continue, right? So why we are giving this example? The exact scenario also occur in case of a processes. There are some resources in your system. Which are resources? Memory is resource, hard disk resource, memory, hard disk, your tape drive, your CPU cycles. These are all resources. Printers, these are all resources. And we are running several processes in our system. There are several processes are running on your system. These processes request these resources. There are limited number of resources only. There might be a chance that this process of making a request and allocating may put the system into deadlock. Just look over here. Suppose this is process 1. Process 1 and this is process 2. There are 2 processes and 2 resources are there. 2 processes are there and 2 resources are there. Correct? Resource 1 maybe hard disk or something. The resource 1 is allocated to process 1. The resource 2 is allocated to process 2. Resource 2 may be memory, which is allocated to process 2. Now, process 1 is requesting resource 2, while the process 2 is requesting for resource 1. So that means the process 1 is holding resource 1 and making request for resource 2. Is it understood? Process 1 is holding resource 1, making a request for resource 2, while process 2 is holding resource 2 and making a request for resource 1. This lead to a circular, this may be this will put in a circular fashion. And here you say the deadlock has occurred. None of the process could able to continue. None of the process could able to continue. You might have marked while working in your computer, sometimes the computer halts and you don't have any option to go back. The system stops over there. So that deadlock sometimes occur in your system, in your computer as well. While working with Windows or some operating system, you will find that it will stuck at a particular place and it will not continue at all. This sometimes is because of the deadlock. Right? This is one more example over here. There is a criminal who has taken a hostage, and the cop is having the criminal's friend, right? The cop is saying that you release the hostage or I won't release your friend. And what the criminal is saying, that I won't release the hostage unless you release my friend, right? So cop, if you think the cop is the thread one, what the thread one demands? The thread one demands resource 2. Thread 1 demands resource 2, but criminal owns the lock. For this resource 2, the criminal is having the lock. For the thread 2, for this thread, for the thread 2, thread 2 demands resource 1, where the thread 2 demands the resource 1, but cop owns the lock, but the cop has its lock. Correct? Similarly, for the criminal's friend, for this one, what happens? The resource 2, the owner of the lock is cop. For the resource 2, owner is this cop, and for this resource, hostage of the criminal, who is the owner? Owner is the criminal. So in this case, none of them can, none of the process can able to continue. They will stand like that, and they cannot release neither the hostage or the criminal's friend can be released if the conditions will be like that only. Is that understood for deadlock? Is the concept understood or not?
Yes, sir.
Yes, sir.
Okay. So now we'll see that the system consists of number of resources. I have already told system consists of number of resources which are distributed among number of competing processes. So you have a limited number of resources which need to be distributed among number of processes. There are various processes are there. Limited number of resources. What are resources? CPU cycles, memory, IO devices, hard disks, tape drive, bus. These are all resources. Understood? Which are being used by the process for running. Those are all resources. Your ALU is a resource, memory is a resource, bus is a resource, CPU is a resource, CPU cycles, memory, IO devices, printer, all these are resources. I hope you can identify which is a resource. Now the resources are limited in nature because it is fixed. You have 2 hard disks or 1 hard disk, you have this amount of memory, you have this number of IO devices. So those are fixed. But you have a lot of processes are running on your system. They might be demanding each of one of these, right? So resources are partitioned into several types. Resources are partitioned into several types. Each resource type Ri has Wi number of identical instances. That means if I have, suppose R1 is hard disk, so there might be 2 hard disks. R2 is pen drive. There might be 1 pen drive. So each resource has how many instances? Identical instances. Correct? So first the resources has been different types. Memory is one type. IO is the hard disk is another type. Printer is another type. So memory is another. There are different types of resource. Second one is how many types of those resources are there? How many hard disks are there? How many printers are there? Those are how many identical resources are present. Is the second one. Now, whenever each process utilizes a resource in only the following, each process utilizes a resource in the following sequence. Whenever a process makes a request, it makes request in 3 steps. Correct? Suppose process 5 want the hard disk. So first it will make a request. It will be allocated so that it will use. After the use, the process must release the resource so that another process can take. Is it understood? So process utilization is done in 3 steps. Request, use, release. Request, use, release. That you remember. So whenever a process makes wants a particular resource, for utilization, that will be done in 3 steps: request, use, and release. Request is if the request cannot be granted immediately, then the requesting process must wait until it acquires the. So it will make a request. If it is available, it will be given. If it is not available, it has to wait. If it will be given, it will use it. After use, it must release the resource. To do these operations, all these are system calls. To do these, the various system calls are there. Is it understood? Is it understood or not?
Yes, sir.
Okay. Okay. Now see here. A set of processes is in deadlock state when every process in the set is waiting for an event that can be caused only by another process in the set. This is the definition for deadlock. It says that a set of processes is in the state of deadlock. When we say a state of deadlock, when every process in the set, whichever process is there, is waiting for an event. They want something to occur that can be caused by only by another process in the set. So there are 4 processes, maybe they are in the deadlock. Every process is waiting a particular event to occur, which will be done by another process, but it is also in deadlock in that state. Correct? So it is a kind of recursive thing. So everyone is waiting for each these to complete. So a set of or another definition is that a set of blocked processes, each holding a resource and waiting to acquire a resource held by another process in the set. So what they are doing, they are holding something. They are holding a resource and they too want to acquire another resource. And the resource that they want, that is held by another process which is holding some resource and requesting for some other process. So let us take an example, a system with 3 CD read-write drives. A system is having 3 read-write drives. Each process P1, P2, P3 hold 1 CD read-write drive and each needs one another. So I have 3 CD drives. There are 3 CD drives. We have 3 CD drives. 3 processes has allocated 3 CD drives. So one for P1, another for P2, another for P3. And each needs another one. So everyone requires also another one. So everyone requires another one means if P1 is holding one requesting for another one, it will never get because each one is holding one. If you could have remembered the what dining philosopher problem, when each of the philosopher will hold one of the resource, one of the chopstick, and they search for the second one, they will never get. It's a kind of deadlock, right? One more thing, a system with one printer. Suppose there is one printer. There is, sorry. So there is one printer and one DVD drive. In a system, there is one printer, one DVD drive. Process PI is holding the DVD. Process PI is holding the DVD. The process PJ is holding the printer. Correct? PI is holding the DVD, PJ is holding the printer. If PI requests the printer and PJ requests the DVD drive, then deadlock will occur. This is exactly similar to the example that I have given for the book. Galvin book and Godbole book, the example that I have given is the same. Right? One more example is for there are 2 processes P0 and P1. P0 makes a lock on wait of A and P1 makes a lock on B. P0 wants to have lock on B and P1 wants to have lock on A. They will never get because they have P0 has already put a lock on A and P0 has already lock on B. So it will never get and this will also never get. They will wait for indefinitely. Right? All these situations are called deadlock situations or deadlock problems. Now it says I hope the deadlock problem is understood.
Yes.
So do remember this deadlock problem what I am discussing, this is not the starvation. Deadlock may have starvation, but starvation may have a chance to continue because they are only having bad luck or priority allocation, which have solutions. But here it says all are waiting for each other and they all are in a difficult situation, right? Now here, look here, it says that a deadlock can arise if the following four conditions hold simultaneously. It says what? If a deadlock occur, very important, if a deadlock occurs, then all these four conditions has to be satisfied. All these four. If any one of these condition is not satisfying, then deadlock is not occurring. So whatever the examples we have given, in those examples, all these four must have to occur. So these are called the necessary conditions for deadlock. These four are called necessary conditions for deadlock. Questions come, what are the necessary conditions for deadlock? The necessary conditions for deadlock are mutual exclusion, hold and wait, no preemption, circular wait. All these four has to occur. Is it understood? These are the necessary conditions for deadlock. What are these conditions are? The first one, it says mutual exclusion. Mutual exclusion says that only one process at a time can use a resource. Other requesting the processes may be delayed until the resource has been released. So it says that one process can use one resource at a time. So you are not sharing the resource. Are you getting me what I'm saying? If you are not sharing the resource, then that is called the mutual exclusion. Only one process at a time can use one resource. If they will share, then the deadlock may break. Correct? If you took the example of the first example that I have given, two students requiring the two books, Godbole and the Galvin book. If they will share, if the process 1 and process 2 are sharing the book, then there is no problem. The deadlock will not occur. Correct? Half of the book he will somebody first student A will reading, or the second half the student 2 is reading. So that if there is a sharing, if the resource can be shared, the deadlock may not occur. But if they are taking it exclusively, I want the resource, but I want it exclusively. I don't want to share with anyone else. Correct? If a process takes a resource, acquires a resource, and says that I will keep it, I will not share with other processes. So then it becomes one of the reason for deadlock. This becomes one of the reason for deadlock. Correct? So you do not have scope for sharing. The process do not have the scope for sharing. Then some are very possessive. That you will become my friend. Once you become my friend, you cannot become a friend for others. It's a mute. That means at a particular time you can have access to one resource only. One process can have access to one resource. The second one is hold and wait. If you look into this those examples, every process is holding some resource and waiting for another resource. Correct? Each of the example that we have, they are holding some resource and waiting for another one. See, it is holding A, waiting for B. This is holding B, waiting for A. This is holding print DVD, waiting for printer. This is holding printer and waiting for DVD. So what it does, in each of the example you will find every process is holding a resource and waiting for the additional resource. If they will release the previous one and request for the next one, then probably the deadlock would have been breaked. Correct? So every process, every process is holding some resource. They are holding a resource, a resource or a multiple number of resources, and they are requesting for additional resources. If you need additional resource, then you have to release the previous ones. Right? So a process holding one resource is waiting to acquire additional resources held by other processes. They are requesting for a resource, and that resource is also held by other processes. That resource is also not free, right? You are holding one process and you want another resource, but that resource is also not free. That resource is also occupied by another process, and that is in a cycle actually. Correct? This is hold and wait. Third one is no preemption. No preemption. What is no preemption? A resource cannot be preempted. If in a situation where the resource cannot be preempted, then it may lead to deadlock. Like in the first example of the cars. If any of the car can go back, then the deadlock could have been resolved. Or the two students are standing in front of the library and waiting for each other. If the librarian will come and snatch the book from one and say that you deposit over here, then you request, then the deadlock could have been break because somebody has to, you are forcibly hello, am I audible now? Am I audible now? Hello. Hello. Am I audible now? Hello.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Okay. So no preemption says a resource cannot be preempted. If this condition is there, what will happen? The processes are waiting for each other and we cannot preempt the resource from the process. We cannot forcibly take out the resources from the process. If two students, those are standing is in front of the library, the example that I have given, in that case, suppose the librarian will come and forcibly snatch the book from somebody and say that you deposit first, then you make a request. If forcibly he can preempt the resource, then the deadlock could have been braked. In a traffic management, the deadlock has occurred. If any of the vehicle will go back, then there might be a chance that the deadlock may have been braked. Right? If in every example, if forcibly we can take out some resource, a preemption could be possible, then the deadlock could have been braked. But in a deadlock, no preemption is one of the conditions. A resource can be released only voluntarily by the process holding it after that process has completed its task. So a resource cannot be preempted. That is a condition, the deadlock. Fourth one is the circular wait. Circular wait is there exists a set of processes, suppose P0, P1, P2 up to Pn, n number of processes are there of waiting processes such that P0 is waiting for a resource that is held by P1. P0 is waiting for a resource that is held by P1. P1 is waiting for a resource that is held by P2. And P2 is holding some resource and waiting for P3, P3 for P4 like that up to Pn minus 1. That means we have, suppose this is P0, P1, P2, like that you have some resources are there. And here you have Pn minus 1. There are n number of resources. N minus 1 is waiting for P0. So P0 waiting for holding some resource and waiting for P1. P1 holding some resource waiting for P2, and like that Pn is Pn minus 1 is holding some resource and waiting for P0. So this is in a circular wait. So a circular wait must occur. A circular wait must occur. So if all these four conditions, try to understand. I am not saying any one of these. Mark it. I am not saying any one of these. If all of these four, these are the necessary conditions, all of these four occurs at the same time, then we say the deadlock has occurred. That means, in other words, I will say, if I could break any one of them, then deadlock will not occur. Correct? So I am saying that if a deadlock occurs, all of these four conditions need to occur. Correct? So is in other words, I may say, if any one of these, if you could able to break any one of these or could not occur, any one of these could not occur, then we could able to break the deadlock. Correct? So now we have a resource allocation graph that says for going to the resource allocation graph. Please hold on for once. Hello. So there is a graph which is used in this for the deadlock detection is called the resource allocation graph, or RAG, resource allocation graph. In resource allocation graph is a directed graph. Um, it has some vertices and edges. Graph has vertices and edges, that you know. The graph has some vertices and edges. What are the vertices? The processes and resources are vertices. The processes or the resources will become vertices. Just look over here. In this example, these are vertices: process 1, process 2, resource 1, resource 2. These are vertices. Correct? So the processes and resources are vertices. What is process? There may be n number of processes, there may be m number of resources in the system, right? So so we have what? We may have some resources are like this, and the processes are diagrammatically represented in these circles, and the processes are represented in form of what? Rectangular boxes. So we may have some edges over here. If a resource is allocated to a process, try to understand. If it is allocated, this is allocation edge. This edge is called the allocation edge. So if there is a edge from resource to process, this is resource. This is a resource. If the resource is allocated to a process, then this is called the allocation edge. This is called the allocation edge. Correct? If a process, if there is an edge from process to resource, if there is an edge from process to resource, then it's called a request edge. It is called a request edge. So if I draw like this, it is a request edge or allocation edge. Can anyone say it is a request edge or allocation edge? This edge is, this is request or allocation? Anyone? Hello?
Request.
It's a request because from process to resource. That means process is requesting to R2. If there is from R resource to process, then we say it is a resource is allocated to process. Correct? So the request is an allocation age or assignment age, we say assignment or allocation age also, right? So when process pi request an instant resource type rj, a request age is granted. So from process to resource, resource to process is assignment age, right? Whenever this is done, when the resource is, this work is done, that age is released. That means now that resource can be given to some other process. Correct? So we use this symbol for process. We use rectangular symbol for resource. But inside the resource, if I have small dots or small boxes over here, that means these are number of instances. Suppose this is one resource R1. R1 means R1 is maybe hard disk. Resource is something, R1 is hard disk. But inside the R1, if I have 4 dots, that means I have 4 hard disks. I have resource R2. Suppose in R2, I have 2 dots. R2, suppose pen drive. So I have 2 pen drives. Correct? So these are the instances. As I said, this is if process to resource, it is a request age. And if it is from resource to process, we say it is a assignment age. Correct? With this, the look over here, the graphs are being drawn. Resource allocation graph is being done. Just look over here. In the first case, the process P1, P2, P3. There are 3 processes are there. Try to understand. There are 3 processes. How many resources? R1 is a resource, R2 is a resource, R3 is a resource, and R4 is a resource. There are 4 resources. Correct? There are 1 instance of R1, 1 instance of R3, 2 instances of R2 are there. Correct? No, none of these 3 processes are requesting for R4 resource. None of these 3 processes are requesting for R4 resource. Now, P1 is requesting for R1. P1 is requesting for R1, but R1 is allocated to P2. P2 is requesting for R3. R3 is allocated to P3. Correct? There are 2 resources which are allocated to P2 and P1. There are 2 resources which are allocated to P2 and P1. Now we'll see whether it is having deadlock or not. First thing is that if all these 4 conditions satisfies, then it is in deadlock. What are the conditions? Mutual exclusion, hold and wait, no preemption, and circular wait. No preemption and circular wait. You can see over here. Is there any circular wait over here? Do you find any circular wait in this diagram? See it carefully and say, is there any circular wait?
No, sir.
No. That means from the RAG, from the resource allocation graph, we can say that this is not in deadlock. This is not in deadlock. I hope it is understood. We'll discuss more on this. Today we do not have much time over here, so I am not going for the other examples. The next class I will tell you that along with this one, I will also tell you that how from the RAG we could able to detect the deadlock. Let's take the attendance. Roll number 2, 3, 4, 5. Roll number 9, 16, 22, 23, 25, 27, 30, 34, 37,
Sir, 16 present, sir.
16 present. Acha, okay.
Sir, 23 also present. I have not renamed myself.
Okay, 23. 41, 42, 45, 48, 51, 73. Acha, Subhasri, your what? Subhasri Samantray, roll number? You have not written your roll number. Okay, respond to only the absent roll numbers are roll number 2, 9, 25, 27, 30, 34, 37, 41, 45, 48, 51, 73. Roll number 32 present. 32 is I have make it present. 23, 16. Yes, roll number 32. Okay. Proceed 16. Okay. I'll end the meeting now.